Imagine you're a bank receiving thousands of credit card applications. How can you automatically decide who should receive a credit card, who is financially reliable, which applicants may default, and which customer attributes actually influence approval? And how can you make these decisions quickly while still being able to explain why the model made them? A decision tree solves these problems by repeatedly asking simple questions. Annual income greater than $110,000? Yes or no? Credit score greater than 690? Yes or no? Approved or rejected? This simple structure involves powerful concepts: how the tree chooses a feature and threshold, how we measure split quality with Gini impurity and entropy, classification metrics, overfitting, pruning, and even predicting continuous values. Welcome to Decision Trees Explained, from zero to complete understanding. By the end of this video, you will understand how decision trees make decisions, how data is recursively partitioned, how the best splitting feature and threshold are selected, how impurity measures work, both Gini impurity and entropy, how to calculate split impurity, how classification models are evaluated with confusion matrices, accuracy, recall, precision, and F1 score, why accuracy can be misleading, overfitting and underfitting, model complexity, pre-pruning and post-pruning, cost complexity pruning and the role of alpha, decision trees for regression using mean squared error, how regression tree predictions are generated, and the key differences between classification and regression trees. Many business problems involve predicting a class. In healthcare, we ask how patient information such as cholesterol, blood pressure, or smoking habits can predict disease risk, readmission, or drug response. In banking and insurance, the questions become credit card approval, fraud detection, and claim approval. In retail, we predict customer churn and campaign effectiveness. In manufacturing, we tackle quality control and predictive maintenance. All of these can be framed as classification problems. Input variables go into a decision model and come out as a class label. We will use credit card approval as our central running example. A bank needs to accurately predict whether an application should be approved and identify the key factors that determine credibility. Current problems include rising risky approvals, high application volume, and slow manual screening. Desired outcomes are fewer risky approvals, faster processing, and a more robust process. Two important predictors are annual income and credit score. Looking at each separately suggests higher scores and higher incomes relate to higher approval probability. But a scatter plot with credit score on the x-axis and annual income on the y-axis, colored by approved versus rejected, immediately reveals their interaction. We can start drawing decision rules by hand. First split: annual income greater than 110,000. Applicants above this line look more likely to be approved, but income alone is not enough. For those above the line, we further ask credit score greater than 690. For those below, we ask credit score greater than 710. The plot divides into four regions, each with a different mix of approved and rejected applications. These partitions become a tree. A decision tree is a flowchart-like predictive structure that repeatedly splits data according to feature-based conditions. The dataset is split into subsets using selected attributes. The same process is repeated recursively. Each split attempts to create groups that are easier to classify. The root node is the topmost node representing the initial split of the complete dataset. A branch represents an outcome of a decision, yes or no, and leads to another node. A decision node is any subsequent node where the data is divided again. A leaf node is a terminal node that provides the final prediction. At a classification leaf, we look at the proportion of each class. The majority class becomes the prediction. The core question is, how does the tree decide which feature to split on and where to place the threshold? The answer begins with impurity. A region where roughly 80% of observations belong to one class has relatively low impurity. A region closer to a 60-40 mix has higher impurity. Impurity represents the uncertainty of the classification decision. Lower impurity means observations inside the node are more homogeneous. Therefore, the objective of every split is to reduce impurity. Trees are built by repeatedly selecting splits that produce purer child nodes. Two primary impurity measures are used: Gini impurity, and entropy. Gini measures how likely an observation would be incorrectly classified if randomly assigned according to the node's class distribution. For binary problems, 0 is completely pure and values near zero point 0.5 are highly mixed. Entropy measures randomness or disorder. 0 is pure, 1 is maximally impure for binary classification. Gini impurity equals 1 minus the sum of pi squared, where pi is the proportion of class I. For a pure node, Gini is 0. For a perfectly balanced node, it is zero point 0.5. When evaluating a split, we must weight the child impurities by their sample sizes. The Gini of a split equals n left over n times Gini left plus n right over n times Gini right. In our sample, we have 6 approvals and 4 rejections. Root Gini equals 1 minus 0.36 minus 0.16, which is 0.48. Testing annual income greater than 110,000, one child has 4 approvals and 1 rejection, Gini 0.32. The other has 2 approvals and 3 rejections, Gini 0.48. Weighted split Gini is 0.40, an improvement over the root. Testing income at 70,000 gives a higher weighted Gini of about 0.476. Credit score greater than 690 also gives 0.40, while 710 gives 0.476. The best splits minimize the weighted Gini. Entropy equals minus the sum of pi times log base 2 of pi. It quantifies disorder. A pure node has entropy 0. A balanced binary node approaches 1. For our root of 6 approvals and 4 rejections, entropy is approximately 0.97. Evaluating the same candidate splits with entropy yields similar rankings. Annual income at 110,000 and credit score at 690 both produce the lowest weighted entropy of about 0.84. Both Gini and entropy therefore lead to the same practical conclusion. Choose the split that most improves purity. Creating the tree is only half the job. We must evaluate whether the model is useful. Treat approved as the positive class. There are 4 possible outcomes: true positive, correctly predicted approval; false negative, should have been approved but was rejected; false positive, should have been rejected but was approved; true negative, correctly predicted rejection. These form the confusion matrix, the foundation of classification metrics. Accuracy is the proportion of correct predictions, true positives plus true negatives over total. But is high accuracy always good? Consider a cancer diagnosis example. 1,000 patients, only 10 have cancer. A model that predicts nobody has cancer achieves 99% accuracy, yet finds 0 cancer patients. Severe imbalance makes accuracy misleading. Recall answers. Of all actual positives, how many did we correctly identify? It equals true positives over true positives plus false negatives. In the cancer example, recall is 0. When missing a positive case is dangerous, recall matters more than accuracy. Precision answers. Of everyone predicted positive, how many are actually positive? It equals true positives over true positives plus false positives. Maximizing recall alone can flood the system with false positives, as in a marketing campaign that predicts everyone will engage. In credit card approval, both false negatives and false positives carry costs, so we need balance. The F1 score is the harmonic mean of precision and recall. 2 times precision times recall over precision plus recall. It is preferable whenever both error types matter. Even after choosing a metric, another problem remains. Decision trees can keep splitting until they become extremely complex. Does a deeper tree always mean a better model? Plot model complexity on the x-axis and performance on the y-axis. Training performance generally improves as complexity increases. Performance on unseen data typically rises, reaches an optimum, then falls. We call the regions underfitting, optimal complexity, and overfitting. An underfit tree is too simple. It fails to capture important patterns and performs poorly on both training and test data. An overfit tree becomes excessively complex. It performs very well on training data, but poorly on unseen data because it has memorized noise. How do we prevent unnecessary growth? Pruning. Pruning reduces tree size by eliminating non-critical sections. Benefits include simplicity, better interpretability, less memorization of noise, and improved generalization. Pre-pruning prevents full growth by setting stopping conditions such as maximum depth, minimum samples per leaf, and minimum samples to split. It is fast and computationally efficient. Post-pruning allows the tree to grow fully first, then replaces unnecessary subtrees with leaves. It is more expensive but evaluates existing branches carefully. Cost complexity pruning is a key method. The complexity parameter alpha controls the trade-off. Small alpha allows larger trees, large alpha forces simpler trees. The procedure generates a sequence of progressively simpler trees and selects the alpha that yields the lowest error on unseen data, exactly the optimal point on the complexity curve. Now, the application has been approved. The bank needs to decide the credit limit, a continuous numerical value. This is a regression problem. Linear regression assumes a linear relationship, but decision trees can model nonlinear, conditional relationships. Genie does not work here because there are no discrete class labels. Instead, we want observations inside a node to have similar numerical target values, so we minimize variation. Mean squared error measures variation around the node's average. 1 over n times the sum of squared differences between each target and the node mean. Lower MSE means more similar values and therefore a better regression split. Weighted MSE across children is used exactly as we weighted Gini. At a regression leaf, the prediction is simply the average target value of the observations that fell into that leaf. A new applicant travels down the tree until reaching a leaf that might predict $40,000, $60,000, $75,000, or $90,000. Classification trees predict categorical labels by reducing impurity with Gini or entropy and output the majority class. Regression trees predict continuous values by reducing variance with mean squared error and output the average target. Putting it all together, the complete workflow is: start from the business problem, define the target, choose predictors, begin at the root, test features and thresholds using Gini or entropy for classification or mean squared error for regression, choose the best split, recurse until leaves, generate predictions, evaluate with the confusion matrix and appropriate metrics, check for under or overfitting, prune using pre-pruning or cost complexity with alpha, validate on unseen data, then deploy and interpret the decisions. Decision trees convert complicated prediction problems into sequences of simple decisions. For classification, they repeatedly reduce impurity. Gini and entropy select the best feature and threshold. Classification performance cannot rely on accuracy alone. Use recall, precision, or F1 according to the business cost of errors. Highly complex trees overfit. Pruning improves generalization. Cost complexity pruning uses alpha to balance performance and complexity. The same idea extends to continuous targets through regression trees and mean squared error. You now have a complete, practical understanding of decision trees, from the first business question all the way to deployment and interpretation. Thank you for watching.